Oh, hi there! I'm planning to cook popcorn, but I do not want one coming out of the saucepan. More so, lots of them. Of course, I'll have less to eat. What do I do? I think I have one nice idea. Escaping popcorns from the pan depend on how I cook them, on what color of flame I use. And like in stars, blue means hot and red means cool. When I shine the blue flame on the saucepan, popcorn cooks and pops out of it. While using the red flame, popcorn cooks and pops but stays inside. Explaining at the subatomic level, popcorns are the electrons and the saucepan is the metal plate. The colored flame, however, is the incident light affecting whether an electron gets ejected. This light consists of photons, which carry the energy required for the electrons to be free from the metal surface. Shining the hot blue light on the metal plate dislodges an electron, hence a photoelectron, because the energy from the photons absorbed by electrons is high enough, thus the possible escape of the popcorn. While using the red light means an electron stays unfazed, given how the coolness of the light possesses a sluggish transfer of energy, prolonging the escape of popcorns. Let's have it in an electromagnetic spectrum, where the frequency of light represents the energy of the photons. Blue light has a higher frequency but with shorter wavelength, indicating how photons can surely eject electrons. The red light has a shorter frequency but with longer wavelength, which signifies less or no ejected electrons. All this explain how the photoelectrons or the ejected electrons are directly proportional to the frequency of an incident light and inversely proportional to the wavelength of it. Despite turning the typical red light into a much brighter shade of it, popcorn stay committed inside the saucepan. Yet having the neutral blue light dimmer than it has been, there can still be popcorns going out the saucepan, only this time, less of them do. It is because bright light meant more photons rather than increasing the energy per photon. Doesn't mean that the light got brighter and so there is a greater possibility to eject an electron. No, but it does, and so with more photons attempting to collide with the electrons, there is a higher possibility of ejecting more of them, though only if each photon already possesses enough kinetic energy. But as incident light intensifies, yet the photons present do not have the right amount of energy required, it becomes useless. Another intensity-dependent demonstration is the photocurrent. This can be seen on how solar panels work. When light incidents on each panel at high intensity, more photons tend to collide with the electrons inside, and the larger the number of photons, the more the ejected electrons, which eventually produce a larger photocurrent in the solar panels. This can then illuminate more objects connected to it.